So again, consider that function, f of x equals x cubed minus 1 all over x minus 1. What is the domain of f? So we got to think about our domain restrictions, right? We want to know, like, all right, well, what can't x equal? So what are our two main domain restrictions we look for?
Dividing over
denominator 0, which is divided by 0, or
square root of a negative.
Right, square root of a negative. So could we divide by 0 here?
Yes.
Yes, specifically for what x value? 1. So x cannot equal 1, or else we would have an undefined value here, okay? Now, this x cubed minus 1 does factor, doesn't it?
Yes.
It's a difference of cubes. So this thing factors to be like, let's see here, it factors to be like x minus 1 times, oh gosh, what is it? Same and then opposite, so it's going to be plus 2x, and then always plus 1 like that, I think. Did I do that right?
Plus x.
Just plus x?
Yeah.
I have to see here, did I factor it at all? Did I bother to factor it? It doesn't look like I did. Okay, so there it is. And then the x minus 1s could cancel. But so, since the x minus 1s cancel, does that mean the domain of f is actually all real numbers then, since the x minus 1 cancels?
No.
No, right. We're trying to figure out the domain of just f. When we cancel things out like that, okay, they're equivalent except for the point x equals 1, because, you know, the original f is undefined there. So when you talk about the domain of f, we want to talk about the original function, not, you know, when it's simplified and stuff like that. We want to talk about the original thing, okay? So the domain here, yes, is from negative infinity to 1 union 1 to infinity, like so. Okay? So let's put this into our graphing calculators and see what this looks like. Okay, so let's see here. Clear out your y1. Okay, and let's see here. Go ahead and graph that bad boy. And yes, everyone graph it. Okay, part of this course is being able to use those graphing calculators accurately. Okay, so did anyone get something that looks like this?
No. I might be.
Anyone get something that looks like this?
I'm not sure.
Okay, because you shouldn't. Okay, Mr. Widmeyer, what? Okay, so you shouldn't. How about, did anyone get something that looks like this?
No.
Did anyone get this?
Screwed up.
Did you really, Joe? Okay, did anyone seriously get this? Anyone get this? No, good, because you shouldn't. You shouldn't have gotten that. No. Okay. All right, did anybody get this?
Yes.
Okay, that is the correct graph. Now, if you got either of those two previous ones, you did not type this thing into your calculator correctly, which is obviously very important, right? So let me go back to my y equals now and reveal what I typed in. Remember, when you have this like kind of rational function stuff, you need parentheses around your numerator, you need parentheses around your denominator, or else it won't graph correctly, right? Your calculator won't read it correctly, okay? Or the way you want it to be read, all right? So we have to be very comfortable with typing in things the way the calculator needs to read it, okay? So this is this, and so we get the correct graph. Now, if you look here, where should we have a problem in our graph? Where should we have a problem in our graph? At x equals 1, right? But if you look here at the graph, at x equals 1, it looks completely fine, right? There's no issue there at all. It looks like it's completely filled in.
Yeah.
Whereas our function should not have any value there, okay, because it's undefined. So there's no asymptote pretty clearly, but there should be a hole there. So how can we kind of see that? Well, if you press the second button, okay, and then trace, that takes you to the calculate menu, right? That little light blue calculate. Well, for me it's light blue. For you it might be like yellow or whatever. If you go to value, which is the first one there, and if you hit enter, it goes to x equals, and there's like a flashing thing. It's waiting for you to give it an x value, and then it will give me the matching y value. So let's just see what happens if we put in 1, and then hit enter, and we get y equals blank. Okay, so this at least makes some sense to us, right? Because at 1, our domain is undefined, and so we should not get some sort of value here. If it gave it like a value of 2, we should probably like scratch our head and say, what the heck's going on here, because that's not the way this is, that's not what we just found out. So, let's go ahead and sketch the graph of this on our paper too. Okay. I'm not too worried about the accuracy, except I do want to put like a little tick mark here at the 1 coordinate on the x-axis, and I'm going to kind of like mimic this, but above the 1 value, we should put a little hole there, right? An open dot, because there should be a hole for that piece. Okay. So then, as mathematicians, and as people, I feel like the story probably goes something like this. I'm not sure, exactly, but I feel like this is probably how it went. It's like we look at something like this and we say, all right, at 1, there's no value, clearly, but if we go just slightly to the left of 1 and slightly to the right of 1, it looks like, as I approach 1 from this side and as I approach 1 from this side, it looks like it's going to a number. Now, granted, at 1, it's undefined, but it looks like it's approaching a number, right? And so we can get pretty close to what should be that y value there, right? Because, again, plugging 1 in, we don't get a y value. But it looks like we could probably figure out what that y value should be if we could fill that hole in. And that's the idea. That's where we kind of enter the idea of limits, right? So limits, we don't actually get to the value of 1 here, but we want to get close to it, very close to it, so we can maybe try and determine what we approach as we get closer to 1, both from the left-hand side and the right-hand side here, what value we approach. And so let's make a little table here. Okay? So I'll make a little like a T-chart, but a side T-chart, like a sideways T-chart, yeah. Okay, so our question is, what happens as x approaches 1? What happens as x approaches 1? That's kind of the question we want to answer here. Okay, so let's get some values that are close to 1. So let's pick. We can't obviously pick 1 to be our x value because that's going to be undefined. Let's pick a value close to 1. Let's say like 0.9, for example. That's pretty close. Okay, and then closer than that is like 0.99, right? And then we could get even closer if we wanted to. We could take a 0.999. Okay, and then I'll leave a little value space for 1 there because we're not going to be able to get to it, but we can, approach it, I guess, what we're looking to see there. So we'll put that in our table. Okay, and then let's see here. I also want, so that's approaching x from the left-hand side. Okay, so here we're kind of approaching in from the left-hand side, but then to go approach from the right-hand side, well, let's see here. That would be like 1.001, right? We want to go just a little bit above 1. And then we'll also do like 1.01, and then we can do 1.1 as well as we kind of like move further and further away. Okay? So, how can we come up with this value, this y value here? How can we fill in this kind of function value here? What should we do now?
Plug it in.
Plug, 0.9 into what?
You can
the function f, right? Now, how should we go about doing that? Trace it on your graph?
Or rather use calculator.
So,
Second calculator value.
Oh, second trace, to go to the calculate value and calculate menu, and go to value. So that's one way to do it. So you can, again, second trace, go to value, and then you can just type in 0.9, and your calculator will spit out 2.71 there for us. Okay, and then we can continue on with that. So value 0.99, 2.97. Excuse me, and then second trace value again, 0.999. We get 2.997. Okay, does anyone know a different way to do this? So, second graph, the table. Okay, now, let me see here. I think your tables are probably all set up like this current table is. Okay, if you press second graph, my current table, it's got like 2, 3, 4, 5, 6, 7, 8, and then it gives me like the matching y values there. The problem is, though, I don't want x values of 2, 3, 4, 5, 6, 7, 8, and so on and so forth, right? I don't want it to count by ones. I want to be able to like put 0.9 in, 0.99, 0.999. Does anyone know how to fix this? How to change this? So, to change your table setup, you press second window, and that gives you the table setup command here. Now, you can change where your table starts. The delta table means you can change by how much like it goes up. So here it's starting at 5 and it goes up by 1 each time. But here's an even more powerful command. If you go down to independent, and instead of having the calculator automatically fill in the values for the independent variable, that is the x variable, we can have it ask us. So highlight ask and hit enter. Now when you go back to your table by pressing second graph, it's blank. And it's blank because it's waiting for us to put values in. So for example, I could type in 0.9, hit enter, and then it spits out the matching y value. I can type in 0.99, and it spits out the matching y value. I can type in 0.999, spits out the matching y value. I can type in 1.001. So there's 3.003, 1.01, and then 1.1. I think this is a little bit faster way, right? It's fewer keystrokes. Okay, if you happen to fill up your table, you can delete out old ones by just pressing the delete button. So if you want to delete this first one here, you just press delete. It's gone now, and you can delete them all out if you want to. Okay, you can also write over top of something. So if I put 9, I can go back up to it, make it 0.9, and now it changes it too. So you can also change values as well. Okay, so that's convenient. So again, we did that in the second window, the table setup there. Okay, and that's how we did the setup there for the table. Okay, so that makes it kind of quick. And so there's us approaching one from the right. We start kind of like this 1.1 is furthest away from 1, then we get closer and closer. Okay? So, all that being said, what does it look like the function is approaching as x approaches 1?
3.
Yeah, it looks like it's approaching the value of 3, right? That's what we want to say. So, in summary right here, f of 1 is undefined, right? It has no value, okay? So the exact value at 1, the value at 1, undefined. But, okay, as x approaches 1, so we don't actually get to 1, but as we get closer and closer, as x approaches 1, f of x moves arbitrarily close to 3. Okay, so what do I mean by arbitrarily close there? Well, what I mean is, Ryan might say, Mr. Wimmeyer, I don't believe this thing goes to 3. Ryan can look here and say, look, the function is off from 3 by 3 thousandths. Okay, on both sides here. That is not the value of 3. That is not 3, and he'd be right. It's not 3. Okay, I could then say to Ryan though, all right, that's fair enough, Ryan. How close do you need it to be in order to convince yourself that it's 3? And Ryan would say, I would need it to be within 1 billionth. And we could just add some more 0.9999999s to our x, right? And eventually we could get it to within a 1 billionth of a difference away from 3. Okay. So as close as anyone would want it to be, to say like, I don't believe this is 3, but I can say, but I'll believe it if it's, a 1 trillionth away from 3. We can get that close. So that's kind of like we can get as close as we need to then say, all right, I guess you're right, it is going to be 3. Okay. So that's kind of the idea.
Instead of saying moves arbitrarily close, can we say approaches?
Yeah, that's fine. Yeah.
I typed in the table like 0.9 loss,
Right.
maybe 1 error, but then I did it again with all the way at the end, and it actually gave me 3.
Yeah, and now if you arrow over and highlight the 3, does it still say just 3? So again, that's an error in your calculator, but it's like basically saying, this is, I can't show you the number of decimal places, it really is, so it's 3. Okay? But you can kind of trick your calculator in that way to give you just what it is. All right, so definition. All right, here's a definition. If f of x becomes arbitrarily close It never actually gets to the value. It becomes arbitrarily close to a single number, and we'll call that single number capital L for limit. Okay? So if f of x becomes arbitrarily close to a single number capital L as x approaches c from either side, and that's important, right? You have to approach the same value from either side. Now, I'm going to underline that because that's important. From either side. The limit of f of x as x approaches c is L. Okay? That's the definition. So that's defining the limit of f of x as x approaches c there. Okay? So that's what we just defined. The limit of x as x approaches c. Okay? So that's a lot of words to write out, right? And mathematicians, rather than writing out long sentences and that are very, verbose and overburdensome or something like that, we use symbols. And so here's that symbolically. Okay, the limit is x approaches c of f of x equals L. That's how you read that. Okay. So, let's try another one. Okay, let's try another one. So let's find, and this is an example here, find the limit as x approaches 0 of x over the square root of x plus 1 minus 1, like that, in the denominator still. Okay, by completing, we'll do it by completing a table, and then graphing to verify. Okay, completing a table and then graphing to verify. Maybe not. Maybe not. Okay. So let's do a little sketch, or sorry, a table. So to fill in this table, let's see here. So what's the value we're approaching? We want to approach x value of 0. So for our table then, our x values need to get closer and closer to 0. Okay, so let's see, I'm going to put 0 kind of like in the center of my table there. And then I need to pick values that are close to 0. So let's see here. So to the left of 0, like negative, well, what would be a good one to pick? Okay, so yeah, I'm going to start with negative 0.1. And then to get a little bit closer than that, what could I do? Add a 0. So I got negative 0.01. That's closer, right? Closer to 0. And then I could do another 0, right? Negative 0.001. Alrighty. And then how about, let's see, from the right-hand side, well, I can just kind of flip it, right? So I'll do 0.01, and then 0.1, like so. Okay, so now we can go to our calculators. All right, let's type this thing in. You guys type it in, and then I'll see if your graph matches mine. Okay. There's what my graph looks like using the standard viewing window of Zoom 6. All right, so everyone was able to get theirs graph to look like mine, right? No problems with the graphing there? All right, that's good. Okay, so there's my table of values right there. That should be at 2.001, I believe. Yeah. Okay. So there's our table of values. So what do we want to say the limit is here, using our table? 2, right? Looks like it's 2. Okay, from the left, we're approaching like really close to 2. Okay, 1.999. Excuse me. And then also 2 from the right-hand side as well. All right. So there we go. So it looks like then by the table, and then we can graph it to kind of verify it too. So if we look here, there's our graph. Again, if we press second trace, we go to value. If we try to type in the actual x value of 0 to find the value there, it gives us a blank. However, if we zoom in on the area, so here's the x value of 0, right? There's x equals 0, so it's like somewhere around here on our graph. If we zoom in on that, so here's a zoom command you guys can use here if you ever saw about this. I like zoom box. It's kind of interesting. Has anyone used zoom box before? All right, so zoom box, you hit enter, nothing happens, right? But that's because if you use your little arrow keys and move them, you'll see that this little like target kind of appears. And what you want to do is kind of like above and to the left of the thing you want to zoom in on. If you hit enter, you can see now it like dropped a little point. And if I go down, you see it's like kind of creating a side of a box, and if you move over to the right then, it creates a box. So now I can zoom in on the exact like kind of area that you want to, you can zoom in on this exact area. So if you hit enter, it kind of zooms into that exact box you just drew. And if you want, you can do it again. Draw another box around it. Because we want to see what's happening right at 0. Okay, now at this point, if I press second trace and go to value and I type in x equals 0, it's still not going to give me anything. But if I press the trace button, okay, now I have a little like cursor here. If I move my left and right arrows, it'll move along my line and give me both the x value and the corresponding y value. And so if I really close here on the left-hand side, I can see that my x value here is just negative and it's almost 2. And if I move right one more, it's again just negative, really close to 0, and now it's really close to 2. If I press right once more, now I've moved to positive, but it's just moved to a positive 2 there. So I've switched from just under 2 to just over 2, so chances are at 0 we want to say that value is 2. So there's kind of graphically how we can do that too. Okay, analyzing it that way.
How far do I have to zoom in for this to become visible?
Yeah.
I don't think it'll ever become visible.
I don't think it ever really becomes like, you never see like a little circle there, no. Yeah, because the calculator, the way it graphs things, it just kind of fills in those dots. Okay. So yeah, unfortunately, no. So then, with our new definition, okay, with our new kind of like notation here, we can now like write this more mathematically. We can say the limit as x approaches 0 of x over the square root of x plus 1 minus 1 equals 2. So that's our answer there. Okay, easy, right? All right, so you guys try one. So you try the limit as x approaches negative 2 of x squared minus 3x plus 2 all over x plus 2. Okay? I want you to evaluate using a table and graph it to verify. Okay, And I'm going to warn you, be careful about how you pick your table values. Okay? Be careful, because we're approaching -2, so make sure that you're approaching -2 correctly from the left and correctly from the right. Thank you. So be careful about how you construct your table here. Okay, you really? That's fascinating. I feel like that's like, and actually we'll see similar to that when we look at another type of limit. An example of a type of limit doesn't exist. What? And make sure you set your cubes up accurately. In fact, I'm going to go ahead and start writing my table just so you guys can, like, check yours versus mine. So let's see here. We're going to approach -2. And to approach -2 from the left, I want to start at something like -2.1. And then -2.01. And then -2.001. Okay? Because it's negative, these values are actually to the left of -2. Okay? And the values to the right of -2 are like -1.999, -1.99, and then -1.9. Okay? So I did this one on purpose because the negatives tend to mess students up. They think that, you know, the 1.9s go over here and the 2.1s go over here. And that's not true. Because of the negatives, the -2.1 is actually less than -2, so that's why you have to flip the order around there. Okay. So if you did that, be careful with the negatives.
What?
Okay. Yeah, the negative can screw things up for people.
Why does this get exponentially large?
Oh, and if you also want to fix your viewing window, just press zoom and then 6, and that'll take you back to the standard viewing window so you can see the graph. And so there's the graph of that, excuse me, of that function.
She said they are giving out tissue boxes.
Oh!
Wow. Right, plastic screens.
And I'll send all my runny noses up to them.
I bet you if I was in prison, they would give me a tissue box.
It costs the taxpayer dollars.
All right, well, thank you, Mackenzie, for the heads up. I guess budget cuts have finally hit the tissues, too, so it looks like I'm going to have to go buy some tissues now. It's okay, though.
Well,
I got tons of money in my bank account, so I'm just...
Would you give us extra credit points if we brought in tissue boxes?
Ooh.
No, sadly, I won't do that.
This isn't Mr. Bingham anymore. Not Mr. Bingham.
I will give you a hearty handshake and a thank you.
Yeah, what about a smelly sticker?
Oh, well, maybe a smelly sticker.
Okay, all right.
That's what I was just saying. I'm going to bring out a case. All right, so, yeah, there you go. Give me all your tissues. All right. So, there's our table. Right? Something like that. Nice. Good job. Caleb is prepared. He's going to run a small clinic over there. All right, so what do we want to say the value is here?
That's a good one.
I think we have to go up the graph really far and then zoom in really, really close.
So if you look at the graph here, and again, let's see, so the negative 2 is like right here, and we can see that the right side of the graph, as I approach negative 2 from the right-hand side, it looks like it goes up, right? It continues to go up, and I can't really see any negative part of the graph, but I think it's because we have to like really, let's see, I got to zoom out some more, I think. So I'm going to use the zoom and go to zoom out. I'm just going to hit enter and give the, aha, and there's another part of our graph. And guess what, where that value of 2 is? It's right here. So as we approach negative 2 from the left, what is this really approaching? A really, really, really negative number, right? Like a big negative number, but in fact a really small negative number, because the bigger it gets as negative, the smaller it really is. So, but anyway, and then as we approach from the right, what do we get to? As we approach from the right, what value are we approaching? Really, really, really big positive number. So what does it look like the left-hand side is approaching? Negative infinity, and the right side looks like it's approaching positive infinity. Okay, so what would we say about the limit here?
That's right, 2 line. X approaches infinity. Oh, is X approaches
Limit as
infinity?
X approaches X from the left or
So remember, our definition here is that if f of x becomes arbitrarily close to a single number L as x approaches c from either side. So again, I'll read it very carefully. If f becomes arbitrarily close to a single number L as x approaches c, in this case negative 2, from either side, the limit of f of x is said to be this. But are we approaching a single number here? We're approaching 2 different numbers. So the limit here does not exist.
no limit.
That's right, no limits, guys. The sky's the limit. Okay, so yeah, no, or limit does not. I was going to say no limit. Limit does not exist.
Yeah, can we spell
Yeah, spell limit's wrong. Limit does not exist.
Limit. Limits not exist.
Okay, and that's our answer here because we're approaching 2 different values from the left and from the right. The limit does not exist. Okay. So, there's that. Continuing on here. So, to summarize, for our study of limits, we are going to utilize a three-pronged approach. Okay, kind of like a trident. All right, three-pronged approach to limits. 3 ways to attack a limit. Okay, so the first one, what we've seen, okay, is the numerical approach. Okay, the table of values. Okay, that's what we did. Second way we're going to do this is the graphical approach, looking at the graph, right? We also did that. Which is why I want you guys to become, comfortable with using these graphing calculators. That's why we have them. They're a powerful tool to help us perform analysis here on this limit. We could use that picture to see that as we approach from the right, our curve goes up to positive infinity. As we approach from the left, or at negative 2 from the left, our curve goes down to negative infinity. So the limit does not exist because there's no one number, no single number it approaches. Okay, so that's the graphical approach. And then the third approach, and this is the one that I don't think we're not going to get to, and for this section of notes, we'll get to it later. It's the analytic approach. Okay, which involves using algebra or sometimes calculus. Okay, but we're not going, obviously we don't know the calculus yet, so we won't be using calculus to analyze limits just yet.
Or I'm assuming I know algebra as well.
Yeah. Okay. This third one is going to be it's going to be like our bread and butter. That's the one we're going to use primarily. Okay, number 3. That's the third approach there. That is the primary one we're going to use. However, should the third one fail, or should we come across something where we can't use algebra or calculus, and there'll be examples I'll show you, so don't worry about what that means exactly right now. But should this approach fail, then we fall back to these 2. Okay, so should this fail, you will not get that kind of question on a non-calculator section of a test or a quiz, right? Should the analysis approach fail, you will then be able to use a calculator to then either do the numeric approach or graphical approach, okay? You'll be able to use that to help you with your analysis. This is, like I said, our bread and butter, though, okay? One other note, okay, 1 and 2 are means of approximating. Approximating a limit, right? We kind of like we're doing some fuzzy math there, I'll say, when it came to this table analysis, right? We didn't, say for certain that something was, the limit was 2. We kind of like saw, like it's pretty close, right? But the analytic approach will give a precise value for the limit. So 1 and 2 are just means of approximating a limit. Okay, we use it to approximate. Okay, cool. So let's try a question here. Let's see. So let's get into another example. Some more analysis. So we want to find the limit as x approaches 3 of x squared minus 4. Okay. So let's graph this real quick. We'll just sketch a graph. This is something we should be able to sketch, right? This is one of our family of function things that we should know, right? We should know what x squared is. It's a parabola, right? What does this minus 4 do?
Shifts it down.
Shifts it down 4. Okay, so from its original position at the origin. So I'm just going to quickly sketch this. Let's see here. So 1, 2, 3, 4, something like this. Okay, I'm going to just do a sketch here. So, actually, maybe I'll be a little more precise. 2, 3, 1, 2, 3. So let's see here. If I put in an x value of 1, 1 squared is 1, minus 4 is negative 3, so 1, negative 3, and negative 1 will also be negative 3. Let's see here. 2 squared is 4, so at 2 it's going to go through 0, and so that's good enough for me. I'll just go ahead and okay, draw that there. Okay, 3 squared would be 9, minus 4 would be 5. So let's see here. So 1, 2, 3, 4, 5. So 3, 5, and negative 3, 5 as well. Okay, all right. So there's a little sketch. I guess I'm going to zoom in on that some more for you guys. Okay. So let's answer some questions. All right, so let's see here. So the limit as x approaches 3 of x squared minus 4, what do we want to say that is? 5. How'd you get it? Yeah, exactly right. At the x value of 3, the function doesn't have a hole there. It approaches 5. In fact, it is equal to 5. And so the limit also approaches 5 because you approach from the left, from the right, it approaches 5. You can check that with your calculator too. Okay, right? If I do x squared minus 4 and go to the table and delete out all these things, if I approach 3 from the left, so I can do the 2.9, 2.99, 2.999. I can do 3.001, 3.01, 3.1. I can see that right around that 3 we do, and certainly as we approach 3 from the left and the right, it looks like it goes to 5. Okay? Just because, I want to be very careful here, just because the function value at 3 is 5 does not necessarily mean the limit is 5. Okay? For a nice, simple function here, that is true. Okay? Yeah, question. So absolutely, in this case, because of the way it's written, we can do a direct substitution, and we'll get to that when we talk more about an analysis, the third approach here. I just wanted to focus mostly on 1 and 2, but absolutely, yes, direct substitution works here in this case. Yep. And so that's actually what I wanted to point out here. So, sorry. So we'll say that for part A there, the limit's 5, and then, what is the function value? What is f of 3 here? It's 5, right? When I plug 3 into the actual function, f3 is 5, so that works. Okay? But this won't always be the case. For example, okay, the function value won't necessarily always be same thing as the limit. So let me make a piecewise function here. We'll say f of x equal to 1 when x is not equal to 2. Okay, and f of x equal to 0 when x is equal to 2. Okay, and I'm going to have us, let's graph this. Okay, so this is so simple of a piecewise function that it's probably more complicated. All right, it's so simple, it's hard. It's so easy, it's hard. So there's our piecewise function here. So let's kind of like think about this. So my function is equal to the value of 1. So if you have a function equal to just a number, what does that like look like?
Horizontal.
It can be a horizontal line through specifically what value?
1.
Through 1, right? This is like saying y equals 1. So y equals 1 is like a horizontal line through 1. Okay? And that's going to be a horizontal line everywhere except at the x value of 2. So let's kind of draw that here. So let's see. I'm going to do a little sketch. Okay. Okay. So let's see here. So everywhere but at the x value of 2, I have a horizontal line at x equals 1. So I'm just going to draw that horizontal line. But then at the x value of 2, what should I draw?
A circle.
An open circle, right? Because it doesn't go to that. And then I'll go to the other side too, and it continues on this way. Okay, so you have this little dot right there. Open circle. So there we graph that top piece, right? Everywhere except at 2, the function value is 1. So function value 1, all the y values are 1, except at 2, it's an open circle there. But then we have another thing here. F is equal to 0 when x is 2. So at the x value of 2, how can I show that f is 0 at 2? What should I draw here? A dot, a little dot, a point. Okay, so there's my graph. That is the graph of f. Okay? Now, what is the limit then as x approaches 2 of f of x equal to? As we approach 2 from the as we approach the x value of 2 from the left, as we approach the x value of 2 from the right, what is the value of the function as we approach 2 from the left and from the right? What's the value of the function?
0.
As we approach it.
It's approaching 1.
As we approach from the left and from the right, from the left, from the right. What's the y value?
1.
What's the y value all along this line? Yeah, it's 1, okay? We are approaching, so as we approach from the left, as we approach from the right, 1 is the value there. Okay, we're approaching. If you don't believe me, we can actually graph this in your graphing calculator. Okay, believe it or not, you can graph piecewise functions in your graphing calculator. Okay, you want me to show you how to do that real quick here? Let me show you. All right, so anytime you have a piecewise function, each piece will go in like your y equals. Okay, so for example, if I want to graph f of x equals this first piece 1, I'm going to put a 1 here. Okay, and I'll put a 0 then in y2. So my two pieces have to go in y1 and y2. Now, obviously, we also have these little arguments over here as well. So how do we do those? Well, you have to divide, okay, and then parentheses, and then that is where we type in our argument. So we want to say divided by x. Okay, now we need the not equal symbol, which actually is a symbol. If you press second math, it takes you to the test menu, and there's the not equals to symbol. So, and then 0. And I think that works like that.
You mean x equals 2?
Whoops, yeah, not 0, sorry, 2. Thank you. And then for this other one, we're going to divide by, and then x, and we're going to use the equal symbol, which again is in the second math test menu, 2. Okay, so it should look like that, and you need parentheses around these little arguments right there. Okay. So we graph that. Oops, and I'm like still way zoomed out there. And of course, it looks like our line goes the whole way through because of the way the calculator draws it. Now, let's see if I zoom in just a slight bit there. Aha! It shows the whole.
Yeah.
Okay, I did zoom 4, which is called zoom decimal. It zooms it in just a slight bit more than like the zoom 6 does. And I have a hole right there at 2. How cool is that? It actually shows it. Okay? And so again, if you wanted to, since we now have this in our graphing calculator, we could go to our table and try and get as close as we want. As close as we want to 2. So I could say like, excuse me, I can say 2. Well, let me do the from the left. So 1.9, 1.99, 1.999, 2.001, 2.01, 2.1. Okay, you can see here in my calculator it's saying 1. As we approach from the left and from the right, it's a value of 1 is the limit there. Okay, why are we getting all these errors over here? Well, let me explain that. So first of all, any questions about the piecewise stuff, I guess? That's how you do the piecewise. So that works for any piecewise function you guys have. You can do it like this. Okay, if you need to use the inequality symbols, you just press second, math, and then there are the inequality symbols right there for you to use too. Okay, so why does this work, or how does it work? The way this works is that your calculator, okay, when you type in x not equal to 2, okay, your calculator will return a value, will spit out a value of 1 if the statement is true, and it will return a value of 0 if the statement is false. Okay, yeah, it's Boolean logic, exactly right, if you're familiar with programming and stuff like that. Okay, so this thing is true for every x value that's not equal to 2. So when your graph goes to start graphing things, okay, every x value that it kind of plugs in to then get the y value, this thing works. y1 is graphed because you're taking your original function 1 and dividing by 1. So it doesn't change it, it just allows you to graph it. But then at 2, what happens? Well, at 2, this thing is now false. So it returns a 0. And then 1 divided by 0, what's that going to be? What's anything divided by 0?
Undefined.
Undefined, so your calculator won't graph that part. Okay, so it won't graph it. And instead it goes down to here, when x is 2, it graphs that 0 thing. Because that's now doing 0 divided by 1. Okay? And anytime x is not 2, it does not graph this value of 0 because you're dividing that by 0 then here. So it's 0 divided by 0, which is undefined. Okay, so that's kind of how that works. You can graph piecewise functions and get nice little holes there. Okay? So yeah. Piecewise functions? Not as far as I know, no. Yeah, but it works. It's something. But I hear what you're saying, though. All right, so there's the limit. And last thing here, what is then f of 2? What's the function value at 2? 0. Okay. So why did I do this example? Why did I show this? I showed this example here where the limit, okay, as we approach 3 from the left and from the right, the limit is 5, and the actual value of the function is 5. Here, the limit as x approaches 2 from the left and from the right is 1, but the actual value of the function at 2 is 0. So why did I do that? Here's the thing, the key point, and this is huge, okay, very important. The existence or non-existence of of f of x at x equals c, okay, has no bearing, okay, on the existence of the limit. So the existence or non-existence of f of x at x equals c. So like the value of the function at x equals c has no bearing on the existence of the limit. Okay, of f of x as x approaches c. I used 2 different stars there, whoopsies, but oh well, you get the idea. Okay, so sorry, I'll get that whole thing on there. So the existence or non-existence of f of x at x equals c has no bearing on the existence of the limit of f of x as x approaches c. Okay, so just because the function has a value at a certain point does not mean that the limit exists there. Just because the function does not have a value at a certain point does not mean the limit does not exist, okay? So these are kind of, they're related, and we treat them kind of like in similar fashions, but they are not the same thing, okay? So you have to keep them separate. Limit, you are approaching. So you have to like get that into your mind. You are approaching. You're not actually getting to it. What are you approaching, okay? So here again, we approach the value of the y value of 1 as we get closer and closer to 2. So as we get closer to 2, our y value is 1. At 2, the actual y value is 0, though, okay, because of the nature of the problem. All right, so questions on that up to that point? Questions on that? I know you will as we go on because it's a difficult concept to grasp, so that's okay. All right. Okay, so we're going to talk now about limits that don't exist. So some limits do not exist, right? We've kind of seen that already. Right? That's right. They're like unicorns. They do not exist.
What?
I'm sorry, Christian. I mean, unicorns do exist. Just not here.
North Korea, they do.
Right. All right, so an example of that. Find the limit. Oops, I'm not going to. I'm sorry. I don't want to use the word limit. I'm going to use the symbolic notation here. So find. Just rewrite the whole thing. Why not? Find the limit. So lim as x approaches 0 of the absolute value of x over x. Like that. Okay. So y'all go ahead and graph that. Okay. Now, do we know where the absolute value command is?
Yes.
Important. Okay. So it's the math button on your calculator, and yeah, over to num, and it's abs. Now, because my calculator has pretty type, it actually puts in little absolute value symbols in there, so it's kind of nice. Okay, so graph that bad boy. So math and then arrow over to num, and it's abs. Math, num, abs.
Oh my goodness, that's so cool.
Okay.
I don't know if that's maybe a problem.
If you want to zoom in a little bit more, you can press Zoom 4. Zoom 4 will let you zoom in just slightly more. Sorry?
I'll find out when I start.
Zoom 6 will take you back to the standard viewing window, Emma.
That broke my calculator.
So, what does it look like the limit is here? As we approach from the left, what's the limit? What's the y value of the function?
-1.
-1. As we approach from the right, what's the y value of the function? 1. So, as we approach from the left, the value is -1. As we approach from the right, +1. So, what would we say the limit is? Are we going to say -1, or are we going to say +1?
Average it to 0.
And the answer is, the limit does not exist. Because they disagree, you can put DNA if you want to. I'm going to put left hand disagrees with right hand. They are arguing. Right, exactly. Imagine that. Okay, the left hand disagrees with the right hand. If you want to draw a little sketch in there, it might not be a bad idea, right? So it looks something like this. And those are open circles there at the intercepts. That's an open circle. Okay. So there's the graph there. Okay, limit does not exist. Okay. Next example. So any questions on that example? Questions on that one? We're good? Okay. So now find the limit as x approaches 0 of 1 over x squared. Well, let's again go to our handy-dandy calculators. You can put parentheses around your denominator here if you wish, but you don't need to because it's just a single term. So, I mean, you don't have to. But, I mean, if you want to just get in the good practice of doing Parentheses around your denominator, not a bad idea. To just be in the habit. Always put parentheses around your denominator, parentheses around your numerator. Okay, I'm going to zoom 6 so it zooms out just a bit more. Aha! So let's sketch that graph. Looks something like that. Yeah. You don't have to sketch it. I just have it there just so that way it's easy to refer to. If you were to look back at your notes, you would have the picture there instead of then having to pull your calculator out to look at it too. Okay, so as we approach 0 from the left, here, right, because here's the x value of 0. So as we move along our graph, approaching 0 from the left, what's happening to our y value of the function here?
It's changing infinity.
It's going up to positive infinity. Okay, good. As we approach as x approaches 0 from the right along our graph here, what's the y value we're approaching? Infinity. So good news. They agree. Here, this one went from -1 on the left to +1 on the right, and we say the limit did not exist because the left hand disagreed with the right hand. Here, the left hand and right hand agree. They're both going to infinity. But the limit does not exist. Okay, why is that? Well, because the concept of limit means that it has a limit, right? It has like a stopping value, right? But infinity does not have a single value. It keeps going, right? It continues. So a limit, infinity is unlimited, okay? So a limit we want to be finite or finite, I think the correct pronunciation. So we want to stop. So limit does not exist because the limit goes to infinity. Same is true for negative infinity too. Okay, so a limit means it has a stopping, like a value. Infinity just goes on forever. Okay, right? That's kind of the problem here. It breaks our kind of understanding or definition of what limit might be. All right, last type of no limit behavior. Okay, so we're going to look at the limit as x approaches, and this one's neat. Well, I think it's neat. But I'm a math teacher, so. Okay, so we're going to take the limit as x approaches 0 of sine of 1 over x. The 1 over x is inside, it's sine of 1 over x, like that. Okay, so let's put that into our calculators here. Make sure, by the way, you are in radians. So I was still in degrees from a previous calculation, so I'm going to switch back to radians. Okay, so sine. All right, graph that bad boy. Okay, so it looks kind of neat. Let me zoom in a little bit more. Do zoom 4. Zoom 4. Okay, it's like kind of pointy there in the middle. But I mean, it looks pretty smooth. Looks pretty smooth. But again, 0, there's some interesting kind of behavior there as we get close to 0. But it kind of looks like it approaches what? What y value might we say it looks like it's approaching? It looks like from the left and from the right it might approach 0, right? It looks like it kind of curves up and comes back down and curves down and comes back up. So maybe 0. Maybe. All right, so let's zoom in some more. So I'm going to use zoom box. Okay, I'm going to zoom in on this kind of like funky area around 0. Okay, so there I'm zooming around that little area around 0 there. So zoom in. And okay, so maybe it's looking a little more complicated than we originally were able to see on the calculator. There's more waves in there. Let's try zooming in again. I'm going to zoom box, and this one I'll make like kind of bigger because it looks like. So I'll use zoom box again. I'm going to arrow all the way up here and hit enter and drop all the way down. Wee, bless you. And then all the way. Wee. Okay, so zoom in there. Alright, and there's like even more waves. And in fact, as we zoom in, it gets more and more packed with these sine waves.
It would be very helpful if the graphic had more pixels.
And so a good sketch of this graph might look something like this. Okay, so like, it's like nice, and then nice, and back out like that. Okay? The problem is here that as you get closer and closer to 0, our sine wave is oscillating. It's like moving. It's like going up and down so much. Okay, that we really can't determine what happens at 0. The closer we get to 0, the more it kind of creates these crazy waves. The more waves are like packed in there. We have no idea exactly what y value we're approaching because it just keeps jumping up and down so much. And so this limit does not exist. Because it's just so crazy. There's actually a term for it, okay? Yeah, oscillation. So the function oscillates. Okay. Now, we can give some information here. For example, we know that this limit value will be no bigger than what? Why not? Why can't it be bigger than 1?
Sine wave.
Yeah, what's the highest value that sine can be? 1, right? We also know that this value, the limit, will be no smaller than what?
-1.
-1. So we know that the function oscillates from -1 to 1. But that's all we can say. That's all we can say. We can't really say what the actual value is. But we at least know it's limited from -1 to 1. Okay? And so those are the 3 types of situations where the limits do not exist. Okay? The limit does not exist if the left hand disagrees with the right hand limit. Okay? Limit does not exist if the limit goes to infinity or negative infinity. And the limit does not exist if the function oscillates, in this case from -1 to 1. Okay? It's a very rare case where we'll see something like this in number 3, but it could happen. 1 and 2 are going to be your kind of like standard ones that you see. Okay, but those are the 3 main ones that we see there. Okay, with pictures. Hooray, pictures. Okay, any questions for me? So again, will this be on tomorrow's test? No, it will not be on tomorrow's test. Okay, will it be on the test after that? Yes.